let's kick off this explainer with a genuinely puzzling question. If you're even a little familiar with physics, you know the golden rule. Like charges repel each other, right? So think about the tiny, incredibly dense nucleus of an atom. It is absolutely packed with positively charged protons. Why on earth aren't they violently pushing each other away? How is this nucleus just squished together without completely flying apart?
To answer that, we've got to take a bit of a spatial journey. And journey inside the atom, building the universe one rule at a time, we're going to start right at that incredibly dense center, zoom outward to the electron shells, and finally look at some mind-blowing real-world applications. We're literally decoding the microscopic rules that build our universe.
And here's the agenda for how we're going to tackle this today. First, the missing mass mystery. 2, naming and numbering elements. 3, arranging the electrons. 4, the quest for stability. And finally, number 5, atomic twins and isotopes. Let's dive right in. Section 1, the missing mass mystery. So, starting at the very core of the atom, early scientists ran into a massive mathematical headache even after they discovered protons. Take helium, for example. It has 2 protons, while a hydrogen atom has just 1. Logically, you'd think helium should weigh exactly twice as much as hydrogen, right? Well, it doesn't. Its mass is actually 4 times that of hydrogen. This missing mass had scientists totally scratching their heads. Was there something else hiding in the nucleus? Enter James Chadwick. In 1932, he finally cracked the puzzle. He discovered a brand new subatomic particle that had a mass almost exactly the same as a proton, but, and here's the kicker, absolutely 0 electrical charge. He called it the neutron. Because they're neutral, neutrons act kind of like cosmic peacekeepers. They step in, create some physical distance between those positively charged protons, and strengthen what's known as the nuclear force. Basically, they keep those repelling protons from blowing the entire nucleus to pieces. So when you look at our 3 foundational building blocks together, it all clicks. You've got the electron with its -1 charge, the proton at +1, and our newly discovered neutron sitting perfectly at 0. The neutron balances the atomic scales. It adds that crucial missing mass to the nucleus without messing up the delicate electrical charge of the entire atom. Moving on to section 2, naming and numbering elements. Now that we've got our physical building blocks sorted out, scientists around the globe desperately needed a unified way to actually talk about them without getting confused. Just look at the sheer contrast between these 2 historical approaches. Back in 1803, John Dalton realized we needed standard symbols, but he came up with these incredibly complicated little pictures, like a circle with a dot for hydrogen or a circle with a C for copper. Honestly, it was a visual nightmare for anyone trying to communicate quickly. Thankfully, in 1813, a scientist named Berzelius suggested a brilliant alternative. Just use the letters of their names. This evolved into the super sleek IUPAC letter system we use today. 1 or 2 letters, first one capitalized, second one lowercase. It made international science completely seamless. But, letters alone aren't enough. We really need to nail down an element's mechanics to uniquely identify it. We do this using 2 key definitions. First up is the atomic number, which we represent with the letter Z. This is the exact number of protons in the nucleus. It is literally what gives an element its unique identity. Second is the mass number, represented by the letter A. This is the total number of protons plus neutrons, the nucleons, all clustered together in the center, which gives the atom its overall weight. And standard notation brings all this together beautifully. You just place the chemical symbol right there in the middle, pop the mass number up on the top left, and put the atomic number on the bottom left. Take carbon, for instance. You've got a big C in the middle, a 12 on top for its mass, and a 6 on the bottom for its protons. Boom! It gives us this complete mathematical summary of an atom's core at a single, highly organized glance. Okay, section 3, arranging the electrons. We've spent a lot of time hanging out in the heavy, dense nucleus. Now let's zoom further out into the mostly empty space of the atom, where these incredibly light electrons are zipping around in very specific energy levels, or shells. Here's the thing. Electrons don't just fly around willy-nilly. They follow the strict Bohr-Bury architectural rules. Step 1. A shell's absolute maximum capacity follows a simple formula, 2n², where n is the shell number. So the first shell holds up to 2, the second holds 8, the third holds 18. Step 2. No matter what the math says about maximum capacity, the outermost shell of an atom can never, ever accommodate more than 8 electrons, period. And step 3, electrons have to fill these shells in a strict stepwise manner. You start from the innermost shell closest to the nucleus and slowly work your way outward. Watching these spatial rules play out is actually pretty amazing. It creates this beautifully orderly pattern. Starting with hydrogen and helium, we fill up that first shell, the K shell, with up to 2 electrons. Once that's full, we move on to lithium and start filling the L shell, just adding 1 electron at a time, until we hit neon, which gets a full set of 8. Then we step out once more to the M shell. It systematically builds up the first 18 elements of our universe in a perfectly predictable, step-by-step pattern. Section 4, the quest for stability. Let's talk about why atoms actually interact with each other in the real world to form things like water, salt, or, well, literally everything around us. It is entirely driven by their unending quest for outer structural stability. The crucial terms to know here are valence shell and octet. The valence shell is simply that outermost shell of an atom that actually contains electrons. And what do these atoms want more than anything else in the universe? They want an octet. An octet is a complete, highly stable configuration of exactly 8 electrons in that valence shell. Atoms with an incomplete outer shell are reactive. They're restless. They are desperately trying to complete that magical set of 8. The real magic is in how they actually go about achieving this. Look at sodium. It has an electronic configuration of 2, 8, and 1. So it's got just 1 lonely electron sitting in its outermost shell. To get to an octet, sodium is more than happy to just ditch that 1 electron, which immediately reveals the nice, full, stable shell of 8 right underneath it. Oxygen, on the other hand, has 6 outer electrons, so it's way easier for oxygen to aggressively grab 2 extra electrons to reach its 8. This specific number of electrons that an atom needs to lose, gain, or share to be stable, that's its combining capacity, also known as its valency.
Section 5, atomic twins and isotopes. Let's zoom out and see how all of this builds into the broader world. Because, amazingly and completely contrary to what early scientists like Dalton thought, not all atoms of the exact same element are identical.
When you compare a standard atomic model on one side with the 3 variations of hydrogen on the other, you spot something super fascinating. Check out those hydrogen atoms. Protium has 1 proton and 0 neutrons. Deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. They are absolutely all hydrogen because they all have exactly 1 proton. Their atomic number is completely identical, but their mass numbers are different because of those extra neutrons. We call these atomic twins isotopes.
And because these twins share the exact same chemical properties but have totally unique physical traits, like their mass, or in some cases being radioactive, they have astounding real-world applications. For example, an isotope of uranium, U-235, is literally used to fuel entire nuclear power plants. Cobalt-60 is used in life-saving radiation treatments for cancer. Iodine-131 treats thyroid issues like goiter. And carbon-14 is the absolute go-to tool for archaeologists trying to determine the age of ancient fossils. These tiny, invisible atomic variations are literally shaping modern science. Now, what's genuinely interesting about the number 35.5, which is the average atomic mass of chlorine, is what it tells us about nature. See, isotopes don't usually exist in neat, equal 50-50 ratios. Chlorine naturally occurs as 2 isotopes, one with a mass of 35 and a heavier one with a mass of 37. But the lighter one makes up about 75% of all chlorine out there in nature, while the heavier one is only around 25%. Because the ratio is so lopsided, scientists have to calculate a weighted average, and that is precisely why chlorine's atomic mass is listed as 35.5, instead of a nice clean whole number. It's a direct reflection of natural reality. Which leaves us with this final, truly profound thought. If simply grasping these microscopic structural rules, understanding the peacekeeping neutrons and the atomic twins we call isotopes, allows us to literally power up entire cities and fight devastating diseases, what other extraordinary universe-building secrets are still waiting to be discovered, right there, inside the atom?